Imagine stepping through a door and finding yourself in a world identical to this one, except for one tiny detail. Maybe you wore blue today, but that you, in that world, chose red. Now imagine not just one door, but infinite doors, opening to infinite versions of you, living out every possible outcome of every decision you've ever faced. A reality where every quantum coin toss, every flicker of a subatomic particle, splits the universe into countless parallel streams of existence. For decades, this idea, the multiverse, has captured our imagination. It's the stuff of science. Fiction, yes, but also a compelling, even beautiful interpretation of the deepest mysteries of quantum physics. It felt grand, limitless, a cosmic stage where all possibilities were simultaneously realized. Narrator. And I looked at that idea, that dizzying infinite expanse, and I said to myself, this feels incomplete. Something about it felt less like a fundamental truth and more like a magnificent, complex accounting trick. What if the entire picture, the endless branching, the infinite versions of you living alternate lives, what if that is just a mirage, a consequence of looking at the universe through a specific, perhaps limited lens? What if, instead of multiplying realities to explain the weirdness of the quantum world, we could find a single, elegant framework, a universe that doesn't need infinite copies to make sense? Today, we're diving into a revolutionary realm of physics. Theories so radical they challenge the very foundation of what we call reality. We're exploring quantum gravity frameworks that propose a jaw-dropping possibility. We might live in just one, utterly unique, interconnected universe. In the next few minutes, you'll see how these emergent models of space-time don't just question the multiverse. They could provide the very evidence needed to dismiss it, once and for all. Whether the idea of countless realities has always thrilled you or felt like an unnecessary complication, this journey will force you to reconsider everything you thought you knew about existence itself. By the end, you'll understand why this isn't just a minor adjustment to our physics textbooks. It could fundamentally rewrite the story of the cosmos and our place within it. To begin to grasp this, we have to let go of our everyday picture of space. We think of space as smooth, continuous, like an empty stage where events happen. But at the unimaginably small scale, the Planck scale, far smaller than an atom, some groundbreaking theories suggest space isn't smooth at all. It's granular. It's made of things. Think of your favorite digital photo. From a distance, it looks smooth, continuous. But zoom in, and you see the pixels, individual points of color arranged in a grid. Now, imagine that, but in 3 dimensions. And instead of static pixels, these fundamental units are dynamic, constantly interacting, weaving together the very fabric of existence. This is the core idea behind loop quantum gravity, or LQG. In this framework, space isn't a passive backdrop. It's an active network, a lattice woven from discrete, tiny loops of quantum information. Researchers are using supercomputers, running simulations with trillions upon trillions of these theoretical loops. And what they're finding is extraordinary. When these loops interlock, knotting together at the Planck scale, they collectively reproduce the smooth, continuous space-time we experience in our everyday lives, across macroscopic distances. The universe in this view is like a cosmic tapestry, woven from quantum threads. Each thread, each loop, carries fundamental information about the geometry of space, tiny units of area and volume. They don't exist in space, they are space. The key insight here, the one that begins to unravel the need for infinite multiverses, is this: quantum geometry itself can emerge from these fundamental loops without ever splitting into separate branches. The quantum state of the universe is encoded in the configuration of this single network of loops. When something quantum happens, like the measurement of a particle, the network doesn't duplicate itself into multiple versions. It reconfigures. It evolves according to the rules of the quantum loops. No parallel tracks laid down for different outcomes. No branching histories spinning off into oblivion. Just one unified fabric, dynamic and evolving, born from these fundamental quantum threads. It's like thinking of water. At the molecular level, it's discrete H2O molecules. But collectively, they form a smooth, flowing river. The river doesn't split into infinite copies when a molecule interacts. The whole system flows and changes, running parallel to loop quantum gravity, offering a similar singular vision of reality is causal set theory. This approach takes a different but complementary view. Instead of focusing on space, it focuses on events and the fundamental relationships between them. Imagine reality is built not from locations, but from moments. Discrete points in space-time like entries in a cosmic ledger. The only thing that connects these moments is causality. Cause and effect. Event A happened, and it caused event B. We draw an arrow from A to B. Event B caused event C, arrow from B to C. These arrows can only point one way, forward in time. Causal set theory treats space-time as a growing network of these events, linked by irreversible causal relations. Think of it as a cosmic family tree, but instead of people, the nodes are space-time events, and the links are lines of ancestry, causality. Simulations based on this simple idea demonstrate that a vast, four-dimensional space-time with the correct structure, the Lorentzian geometry described by Einstein's relativity, can emerge naturally from these causal sets. Just like LQG, the power of causal set theory lies in its ability to handle quantum uncertainty within a single structure. Instead of each quantum event, each potential choice in the universe's history, spawning a new universe to accommodate every outcome, uncertainty becomes a feature of the causal network itself. Which event comes next? Where does the next point appear in the growing network? The quantum rules govern the probabilities of these additions, but they are additions to one network, one history. The universe evolves as a single, self-consistent story. No branching paths like a fork in the road. Just one cosmos, adding new chapters, event by event, knitting itself together through the unbreakable logic of cause and effect. If this kind of mind-blowing science, the kind that makes you rethink everything you thought you knew, excites you, then you're in the right place. Make sure you subscribe, because we dive into discoveries like this, the ones pushing the absolute boundaries of human knowledge, every single week. Now, to truly appreciate the revolutionary nature of LQG, causal sets, and the other theories we're about to explore, we need to rewind. We need to understand why the multiverse became such a prevalent idea in the first place. Our story takes us back to 1957, and a brilliant young physicist named Hugh Everett III. He was wrestling with one of the most perplexing issues in quantum mechanics, the measurement problem. Why does a quantum system, which exists in a fuzzy superposition of possibilities, like Schrödinger's half-dead, half-alive cat, suddenly snap into a single definite state when we observe it? The standard explanation, the collapse of the wave function, felt arbitrary and mysterious. Everett proposed a radical solution. The wave function never collapses. Instead, at the moment of measurement, the universe itself splits. Every possible outcome of the quantum event is realized, each in its own separate, non-interacting universe. If the cat was half dead and half alive, the universe splits into one where the cat is alive and one where the cat is dead. The observer, too, splits, becoming part of the respective branches. This is the many worlds interpretation. It elegantly resolves the measurement problem by simply saying all possibilities happen, just in different realities. Decades later, another monumental theory arrived, string theory. While aiming to unify all fundamental forces, including gravity, it inadvertently opened another door to multiplicity. String theory posits that fundamental particles are not points, but tiny vibrating strings. The way these strings vibrate determines the particle's properties, but the theory requires extra spatial dimensions, often 10 or 11 in total, curled up too small for us to see. The problem is, These extra dimensions can be curled up in an almost unimaginable number of ways. Each way of compactifying the dimensions leads to a different possible vacuum state for the universe, with different physical laws, different particles, different constants of nature. This is the string theory landscape, estimated to contain a staggering 10 to the power of 500. That's a 1 followed by 500 zeros. Possible universes, each with its own unique physics. Suddenly, parallel universes felt not just plausible, but almost an inevitable consequence of our leading candidate for a theory of everything. Adding fuel to the fire, experiments in quantum, optics exploring decoherence, the process by which quantum systems lose their wave-like properties and start behaving classically, seem to confirm the idea that quantum systems avoid collapse by interacting with their environment. Proponents of many worlds interpreted this not as collapse, but as the environment itself becoming entangled with the system, effectively leading to the branching process where different outcomes become segregated in different realities. These results pushed many skeptics toward accepting a vast, perhaps infinite multiverse. Yet for all their explanatory power regarding quantum weirdness, or the vast possibilities of string theory, none of these ideas truly reconcile quantum mechanics with gravity in a seamless way. General relativity, our magnificent theory of gravity, treats space-time as a smooth, continuous, flexible manifold. Quantum mechanics, on the other hand, deals with discrete packets of energy, probability, and fundamental graininess. Efforts to unify them, postulating extra dimensions we can't see, or hidden mother universes, often felt like patchwork solutions, adding complexity without addressing the core conflict between a smooth reality and a fundamentally discrete, probabilistic one. This is precisely why the new quantum gravity frameworks we're discussing are so radical. They don't just offer new interpretations of existing quantum oddities or postulate hidden realms. They promise a seamless unification of gravity and quantum mechanics by rebuilding space-time from first principles, from the ground up, without needing to multiply realities. And that's where things get truly strange and incredibly exciting. Enter asymptotically safe gravity. This concept, first suggested by the legendary physicist Steven Weinberg in the 1970s, takes a completely different approach to handling gravity. At the incredibly high energies present near the Planck scale, the very realm where quantum gravity effects become dominant. The problem is that, unlike other forces, gravity's quantum description tends to lead to infinities in calculations at high energies, making it impossible to predict anything. It's like trying to measure a smooth curve with an infinitely jagged ruler. The answer just blows up. Asymptotic safety posits that, counterintuitively, gravity's behavior at these extreme high energies doesn't become uncontrollably infinite. Instead, it approaches a kind of stable point, a non-trivial ultraviolet fixed point. Think of it like a turbulent river getting smoother as it approaches a waterfall, high energy point, or a complex mathematical equation that simplifies and becomes predictable when the variables become very large or very small. Quantum fluctuations, usually the source of infinite headaches in gravity calculations, effectively regulate themselves. This makes gravity renormalizable, allowing us to perform meaningful calculations and make predictions at the quantum level. Using sophisticated mathematical tools like functional renormalization group equations, researchers, notably led by Martin Reuter and Roberto Percacci, have found strong evidence that this fixed point exists. If gravity is indeed asymptotically safe, it means we have a single, consistent, predictive quantum gravity theory that works from the largest scales, the cosmos down to the smallest quantum jitter, and crucially, no extra universes required. No splitting, no branching, just one universe where gravity behaves predictably even at the quantum edge. Another path to a single emergent reality is taken by causal dynamical triangulations, CDT. Like CST, CDT starts with discrete building blocks, but here they are tiny four-dimensional pieces of spacetime called simplices, the 4D equivalent of triangles or tetrahedrons. The key is that these simplices are glued together according to strict rules that preserve causality. ensuring that cause always precedes effect. Imagine building a universe out of tiny, fundamental Lego bricks, but you can only snap them together in ways that make sense chronologically. Large-scale computer simulations of this process reveal something remarkable. Starting from these simple local rules, a vast, four-dimensional universe with a smooth geometry, resembling the space-time, general relativity, emerges naturally. At macroscopic distances, it looks like the smooth universe we know. But at the Planck scale, the structure becomes fractal, irregular with an effective dimension closer to 2. This provides a compelling picture of space-time as an emergent phenomenon, its properties changing depending on the scale at which you look at it. And again, CDT never produces separate branches. The simulation starts with an initial configuration and evolves forward, producing a single, dynamic, emergent entity. The universe isn't splitting, it's growing and organizing itself, according to these causal gluing rules. When you combine these ideas, LQG's quantum loops, CST's causal networks, CDT's geometric assembly, a powerful pattern begins to emerge. What if space-time itself is the result of a kind of cosmic computation? Not computation in space, but space as computation. In these models, the fundamental rules governing the interaction of loops, the growth of causal sets, or the gluing of simplices are like the algorithms or source code of the universe. Quantum uncertainty isn't resolved by creating parallel copies. It's encoded within the assembly rules themselves. The universe evolves like a single program running. It might have complex branches within the code, conditional statements, if this, then that. But it's one program executing, producing one output history, not parallel processes running simultaneously on infinite different computers. Numerical evidence from these simulations is starting to show that the predictions of general relativity naturally appear at large scales, a strong hint that this approach might deliver a complete theory of quantum gravity that describes reality from the smallest to the largest scales. But at the heart of these ideas, connecting the geometry of space to the mysterious world of quantum mechanics, lies an anomaly so profound it could upend everything we thought we knew about reality and entanglement itself. Now prepare for a concept that sounds like pure science fiction, but is at the cutting edge of theoretical physics. The ER-EPR conjecture. Proposed by brilliant minds Juan Maldacena and Leonard Susskind, this conjecture posits something truly mind-bending. Einstein-Rosen bridges, theoretical tunnels through space-time, often called wormholes, are fundamentally the same thing as EPR pairs, particles that are quantumly entangled. Remember entanglement? It's that spooky action at a distance Einstein famously disliked, where two particles are so deeply linked that measuring the state of one instantly tells you the state of the other, no matter how far apart they are. It's one of the most baffling aspects of quantum mechanics. Wormholes, on the other hand, are solutions to Einstein's equations of general relativity, theoretical shortcuts through the fabric of space-time, connecting distant points. ER-EPR says, these are two sides of the same coin. Every entangled particle pair, no matter how far apart, is connected by a microscopic wormhole, a tiny thread weaving geometry out of quantum links. In this picture, the entire fabric of space-time isn't a pre-existing stage. It's a dynamic, emergent structure, built from the network of quantum entanglement connecting everything in the universe. It's a kind of relational geometry, where distance and connection arise from these quantum links. Recent tabletop experiments in quantum optics, demonstrating phenomena like entanglement swapping and teleportation, while not directly proving ER-EPR, hint strongly that entanglement patterns could indeed be the underlying basis for space-time connectivity. This perspective is a powerful blow against the many worlds idea. Why? Because it dissolves the need for branching universes. Quantum uncertainty isn't something that forces reality to split and export outcomes into parallel timelines. Instead, that uncertainty, those probabilistic outcomes, are encoded directly in the structure and dynamics of the single, entangled network that builds our universe. When a measurement occurs, The entanglement network that is space-time doesn't duplicate. It reorganizes. It updates. The information encoded in the quantum links shifts, leading to a definite outcome for the observer, not by creating new realities, but by changing the configuration of the only reality that exists. The many worlds narrative, with its endless duplication, falls away, replaced by a single, breathtakingly complex dynamic tapestry of information. Observers share correlations, not across disjoint realms, but within one evolving, interconnected cosmos. Let's just pause and reflect on what this means for us, for concepts we hold dear like free will, determinism, and the very nature of choice. Take a breath. If reality is a single, deeply entangled network, a unified fabric woven from quantum connections, rather than an infinite tree of branching timelines, our place in the cosmos shifts dramatically. In a multiverse, every decision you make spawns countless alternate selves, each living out a different choice. The you who chose coffee, the you who chose tea, the you who stayed in bed, they all exist somewhere. Your individual choice feels, in a way, diluted, less unique. But if there is only one unfolding reality, one single timeline shaped by the fundamental rules of entanglement and emergence, then your decisions, your actions, bear the full weight of their consequence on that one shared reality. Personal responsibility isn't offloaded onto theoretical parallel versions of you. It rests squarely on the shoulders of the single you, right here, right now. That's not just physics getting serious. That's existential gravity. The emergent space-time picture, especially in models like causal sets and entropic gravity, also invites a deeper question about something we take for granted: time itself. If reality is fundamentally information, and space-time emerges from its organization or computation, is time just a sequence of informational updates, a measure of how the cosmic computation is progressing? If so, the flow of time, our experience of past, present, and future, might not be a fundamental dimension reality exists in, but rather an emergent property of the quantum computation or the reorganization of the entanglement network. It arises from the process, not an external clock. If you've made it this far, diving headfirst into ideas like quantum loops weaving space-time and entanglement being wormholes, you are clearly someone fascinated by the deepest questions about existence. Hit that like button and let us know in the comments. What's your gut feeling about the fundamental nature of reality? Is it a simulation? Higher dimensions? An information network? Let's talk about it. Now let's push the boundaries even further and dive into one of the most mind-altering concepts of modern physics, one that ties many of these emergent ideas together: the holographic principle. Initially championed by brilliant thinkers like Gerard 't Hooft and Leonard Susskind, this theory takes inspiration from an unexpected source: black hole thermodynamics. For decades, physicists puzzled over a paradox. Black holes are regions of space-time where gravity is so strong, nothing, not even light, can escape. It seemed like information about anything falling into a black hole would be lost forever, violating a fundamental rule of quantum mechanics. But Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, a measure of disorder, or information content. And here was the paradox: the entropy of a black hole scales not with its volume, as you'd expect for something containing information in 3D space, but with the area of its event horizon, the 2D surface boundary from which nothing can escape. This was a major breakthrough. It suggested that the total information capacity of a region of space might not be proportional to the space it occupies, volume, but rather to the surface that contains it, area. This concept gave rise to the bold holographic principle, the idea that the information content of any region of space can be encoded, like a hologram, on a lower dimensional boundary surrounding it. Our 3D reality, perhaps even 4D space-time, could be a projection from information encoded on a 2D surface at infinity. This notion is now central to connecting gravity and quantum mechanics. In a powerful mathematical framework known as the ADS-CFT correspondence, anti-de Sitter space, conformal field theory. Physicists showed that a theory of gravity in a certain type of higher dimensional spacetime, ADS space, can be mathematically exactly equivalent to a quantum field theory, living on its lower dimensional boundary, CFT. Everything happening in the bulk spacetime is perfectly described by the physics happening on the boundary. To put it simply, everything we perceive as happening in our familiar 3D or 4D universe might actually be a projection of information encoded on a distant, lower dimensional boundary. Our reality could be a kind of illusion, a complex emergent phenomenon arising from the rules and constraints defined on that boundary. And this could fundamentally challenge our perception of the multiverse. If the universe operates according to holographic principles, then the concept of a physical multiverse, an infinite number of separate, parallel universes, may not be a literal description of reality. Instead, what we perceive or calculate as a vast array of separate realities, like the string theory landscape or the branches of many worlds, could actually be a projection artifact, an illusion arising from the incredibly complex way the encoded data of a single, boundary-defined reality is interpreted or rendered. In this framework, what seems like an endless cosmos of divergent timelines could simply be a reflection of how the data of one universe is encoded, processed, and projected into the reality we experience. The many worlds interpretation, once seen as a compelling explanation for quantum randomness, might now be viewed as a mathematical convenience, a powerful tool for calculating possibilities within the holographic projection, but not implying the physical existence of all those calculated worlds. Like rendering different camera angles from the same 3D model, they show different perspectives, but come from one underlying dataset. To dig even deeper into this idea that the multiverse might be a mathematical tool rather than a physical place, let's pivot to another transformative perspective within quantum mechanics itself: quantum Bayesianism, or QBism. This interpretation, developed by physicists like Chris Fuchs and Rudiger Schack, offers a radically different view of the wave function, the central mathematical object in quantum mechanics that describes the state of a system. Instead of treating the wave function as an objective entity describing the physical system itself, QBism redefines it as a tool for an observer to update their personal beliefs and expectations about the system. In QBism, the wave function is not a description of external reality. It's a reflection of an observer's knowledge, their degrees of belief about possible outcomes. It's a subjective framework for managing uncertainty. Think of it like a weather forecast. A forecast isn't an objective description of the atmosphere everywhere. It's a prediction, a statement of belief about the probability of rain, based on the meteorologist's data and models. Different meteorologists with slightly different data or models might have slightly different forecasts, but they're all describing the same atmosphere. In this context, the branching worlds of the many worlds, interpretation lose their foundational significance. Instead of each quantum measurement physically splitting the universe into multiple, real branches, quantum events in QBism are seen as moments where the observer gains new information and updates their beliefs. Each outcome doesn't create a separate universe. It simply refines the observer's understanding of the single universe. Reality doesn't split. The observer's perception and knowledge of reality evolve based on the new information gained through measurement, following the rules of quantum probability. The multiverse, from a QBist perspective, isn't a physical fact about the universe's structure. It's a bookkeeping device, a mathematical framework used by the observer to track different possible outcomes based on their knowledge and the quantum rules. What's important is that the world doesn't branch into multiple realities. Instead, the observer's perception and predictive power about the world update according to quantum rules. The many worlds interpretation becomes more of a mathematical abstraction, like a complex probability distribution, useful for calculating possibilities, but not necessarily implying the physical existence of all those calculated paths. Both the holographic principle and QBism, from vastly different starting points, gravity, space-time structure, and quantum interpretation, you arrive at a strikingly similar conclusion. They treat the multiverse not as a physical reality, but as a mathematical convenience, a powerful tool for modeling probability or representing information, but not requiring infinite physical copies of our universe. This perspective offers a stunningly clean resolution to the multiverse debate, sidestepping the profound philosophical and physical issues raised by postulating an infinite number of parallel worlds. Instead of endlessly speculating about countless alternate timelines and how they might interact, or not, we begin to see the multiverse concept as a convenient mathematical tool used either to model quantum uncertainty, QBism, or to represent the information encoded on the boundaries of space-time, holography. If future experiments in quantum gravity, investigations into the ER-EPR conjecture, or probes of holographic duality and emergent space-time models continue to confirm these ideas, we could be approaching a profound moment in the history of physics, a discovery that could shatter the concept of the physical multiverse entirely. Rather than an infinite cascade of parallel universes, a sprawling cosmic tree, we might find that our universe, one single reality, is far more interconnected, self-contained, and fundamentally informational than we ever imagined. The quantum world isn't branching off into separate realms. It's a single dynamic self-organizing web of correlations, entanglements, and evolving information. But the twists in this story don't end here, because what follows next goes even deeper, questioning the very origin of gravity itself. In 2010, the brilliant theoretical physicist Eric Verlinde introduced a radical proposal. He argued that gravity might not be a fundamental force at all, not something that exists at the deepest level of reality, alongside electromagnetism or the strong nuclear force. Instead, he proposed that gravity could be emergent, an entropic force, born from the statistical behavior of microscopic information, much like temperature or pressure emerge from the collective motion of countless atoms. Here's the core idea. Systems in nature tend towards a state of maximal entropy, a state of highest possible disorder, or, more precisely in information theory, a state where information is maximally distributed and correlations are minimized. Verlinde argued that gravity is simply the universe's way of trying to maximize entropy. Matter, in this view, doesn't exert a mysterious pull on other matter across empty space. Instead, the presence of matter creates an imbalance, a gradient, in the distribution of fundamental information. Gravity is the force that emerges as the system attempts to redistribute that information to restore equilibrium, to smooth out those information density differences. Matter isn't causing gravity. It's responding to the system's drive to maximize information entropy. Think about dropping a drop of ink into water. The ink doesn't instantly distribute itself evenly. It starts concentrated. The natural tendency, driven by entropy, disorder, mixing, is for those ink molecules to spread out until they are uniformly distributed. Gravity, in Verlinde's model, is an analogous emergent force driving the uniform distribution of information. Verlinde's theory doesn't exist in isolation. It plugs seamlessly into other mind-bending frameworks we've discussed, like the holographic principle, information encoded on boundaries, and entanglement-based geometry, space-time built from quantum links. Together, they suggest something even more profound, that space-time itself is not the fundamental stage. It is the equilibrium state, the emergent form of a deeper quantum informational system constantly trying to balance itself. In this new model, the universe isn't events happening in space-time. It is space-time, emerging from the byproduct of data organizing itself. And here's where it gets shockingly concrete. One of the biggest mysteries in astrophysics is the problem of galaxy rotation curves. Galaxies spin so fast that, based on the amount of visible matter, they should fly apart. The standard explanation is that there must be some invisible, undetectable substance adding extra gravity, dark matter. But recent astrophysical studies have applied Verlinde's emergent gravity ideas to this very problem. And astonishingly, His model produces those same observed galaxy rotation curves without needing a single dark matter particle. The gravitational pull in his framework isn't caused by some unseen mass. It's caused by how information is distributed around the visible mass and the system's drive to maximize entropy. And so far, the model fits observational data surprisingly well. This leads to a stunning possibility. Gravity and the space-time fabric we inhabit are not built-in features of reality's deepest level. They are emergent, fluid consequences of how fundamental information behaves, how it organizes and distributes itself. And if that's true, the implications for the multiverse are profound. Why? Because an emergent universe, one that arises from the collective behavior of information bits seeking equilibrium, doesn't need to split to accommodate quantum outcomes. There's no foundational mechanism demanding that every quantum choice creates a new timeline. Instead, all possibilities, all uncertainties are processed and resolved within one evolving, self-regulating system of information. The cosmos becomes self-organizing, yes, but also singular. No branching paths, no parallel Earths, no ghost. Versions of you living out alternate lives where you took that other job or married that other person. And this is where it gets even more mind-bending. Some theorists are now pushing the envelope further, proposing that quantum fluctuations, the inherent randomness, the jitter, the uncertain blips and bursts at the heart of quantum mechanics, aren't fluctuations of energy or particles in a vacuum. Instead, they're fluctuations in a hidden informational network, the very structure that builds reality. According to this view, the uncertainty principle doesn't reflect a chaotic, branching reality. It reveals the fundamental limits of knowability, the inherent fuzziness embedded in the informational structure of the universe itself. So when a quantum event happens, it's not that a universe splits. It's that a piece of the universal information ledger has been updated, refined, or interacted with. Every outcome is not the birth of a new world, but the refinement and evolution of this one world. This flips the multiverse concept on its head. What if we never needed infinite universes to explain quantum weirdness, the measurement problem, or the vastness of the string landscape? What if we only needed to understand how information behaves at the most fundamental level? The universe, in this view, is not a sprawling, branching tree of diverging timelines. It's a single flowing computation. The laws of physics are its source code. Quantum events are write operations, updates to the cosmic database. And gravity? Gravity is like the emergent heat or organization pattern rising off the processor as the computation runs. So maybe the multiverse isn't the answer. Maybe what it is the question. A placeholder for our current ignorance about the true nature of reality. A reflection of our tendency to multiply possibilities into physical realities rather than seek a deeper, unified logic. Because if the universe is informational at its core, then everything, matter, energy, space, time, even the mysterious pull of gravity, is just the way information organizes itself. Not across many worlds, but within one, single, interconnected reality. And if that's true, we're closer than ever to understanding not just the fabric of reality, but the loom it's woven on. We began by asking a bold question. Could a quantum gravity theory finally end the multiverse debate? After traversing a labyrinth of radical ideas, from space woven from discrete loops and time built from causal events, to entanglement being wormholes and reality emerging from information and entropy, we're left with a startlingly coherent alternative. A universe that doesn't branch into infinite copies, but one that emerges from the deep, elegant logic of quantum information itself. This isn't a patch applied to old problems. This isn't just a new interpretation tacked onto an outdated framework. This is a paradigm shift, a fundamental rethinking of reality's foundation. Instead of infinite timelines splitting at every quantum choice, we see a single unified cosmos, one that evolves through discrete updates, not eternal branching. In this vision, computation replaces wave function collapse, entanglement replaces spatial separation, and information-seeking equilibrium replaces cosmic chaos. Reality is not a sprawling, disconnected multiverse. It's an unfolding algorithm, a single dynamic process governed by fundamental informational laws that we are only now beginning to glimpse. The implications of this shift are profound, not just for physics, but for us. First, it restores something we often lose in multiverse: thinking agency. If every possible version of you already exists somewhere, having made every possible choice, does your choice here, now, truly matter in a fundamental way? In a physical multiverse, your reality is just one leaf on an infinite tree. But if there is only one unfolding reality, one you, then you bear the full weight, the full significance of your actions and decisions. Every choice you make helps shape the unique timeline we all share. That's not just physics. That's existential gravity pulling at your very being. Your life, your choices are not diluted across infinities. They are singular, and they matter deeply. Second, it reshapes the quest for a theory of everything. Maybe it's not about finding a single set of laws that governs all possible worlds. Maybe it's about decoding the fundamental operating system of this universe, understanding how bits of information become atoms, how entanglement becomes the geometry of space, how the tendency towards entropy becomes the force of gravity. The universe may not be an object to be passively observed from the outside, but a complex, emergent process to be understood from within. And third, it reframes the role of the observer. In many physics interpretations, especially those favoring the multiverse, the observer is often seen as a passive recorder, or worse, the very cause of branching. But in this emergent universe, based on ideas like QBism and EREPR, observation is an active interaction. It's not splitting worlds. It's a participatory event that rewires and updates the informational structure of the single reality we're embedded in. Measurement doesn't spawn new universes. It reorganizes the information fabric of the only one that exists and updates the observer's knowledge within it. So perhaps the multiverse was never the final answer to the universe's mysteries. Perhaps it was a question all along, a placeholder for our ignorance, a mirror we held up to our deepest uncertainties about quantum mechanics and gravity. And now, under the weight of these powerful new emergent theories, that mirror might be cracking, revealing a deeper truth. As quantum gravity takes shape and these emergent models gain traction, we may be witnessing the end of the multiverse as a physical concept, not as a loss, but as a profound revelation, one that replaces the dizzying, perhaps existentially overwhelming, infinity of branching worlds with something even more mysterious, more beautiful, and perhaps more meaningful. A singular universe, conscious of itself through the intricate dance and organization of information. And that, my friends, is where the real story of reality truly begins. If this deep dive into the potential end of the multiverse and the rise of a single, emergent reality has changed how you see the universe, you absolutely won't want to miss what's next. Make sure you subscribe and turn on notifications so you don't miss it. In our next deep dive, we'll tackle a question that has haunted physicists and philosophers for centuries. Does time even exist? We'll explore mind-bending theories that challenge time's reality and show how quantum gravity might just reveal that our everyday experience of time is yet another illusion, another emergent feature of a deeper, timeless reality. This journey into the fundamental nature of existence is just beginning, and exploring it together is one of the greatest adventures imaginable. Thanks for watching, and we'll see you in the next deep dive.